Technology and Black Excellence Matters event. Today we are honored to have Dr. Rhonda Franklin from the University of Minnesota with us today. As our growing series, it's now become the Tech Talk series, and we're thrilled to bring a variety of speakers from technical fields and universities to share their research and developing technologies with us. As part of the Women in Technology group, we're excited to have more and more representation from women in STEM fields and to share their developments, their research, their professional developments, and their careers with us. So with that, I'll hand it over to Amr, who is leading our Black Excellence Matters group.
Greetings, Dr. Rhonda Franklin. I just realized today that it's been 5 years since we met at WamiCon conference, IEEE conference in Clearwater. And I was presenting part of my dissertation work, and she came up to me, and I was thinking she was excited about my work. And she asked about my advisor, and apparently he was one of the students she mentored while she was at University of Michigan. And she gave me an advice that till today, it's actually even more applicable. And at the time, is not what I wanted to hear, which was make sure you actually plan for um, taking time for yourself, and your self-being and self-health is as important as achieving your goals and degrees and what so. And with the midst of the pandemic, we actually feel that even more. Um, but more importantly, today is about her. She's going to come and talk to us about 6G, and she's a professor at University of Minnesota of millimeter wave, and she's also very engaged in terms of solving and being part of the solution when it comes to STEM, also in terms of underrepresented minorities. And I'll leave you with the one quote that she shared with us, saying that diversity doesn't mean that everyone gets a smaller piece of the pie because there are more people. Diversity helps grow the pie and increase the radius. So we end up with a bigger pie to start out with. So with that, I'll just pass the mic to Dr. Franklin, and excited to hear your presentation. Thank you.
Thank you very much, both of you, for very nice introductions. I thought I would. My talk is going to be about an enabling technology, which is what my group tends to work on. And our applications are millimeter wave communications and also nanomedicine, which is an area that I've gotten involved with lately because of my work in millimeter waves for communications. The picture on the left is what Minnesota looks like in the summer. You'll see it's really quite beautiful. And this, my building is actually behind the one that you can see on the left. So you can't actually see it from here. And this is a light rail that was developed since I came here to be part of the faculty, probably about 5 years ago. This is my building. We are part of the College of Science and Engineering. We have all science except biology and all disciplines of engineering. In my department, we're about 45 faculty. We have about 670 plus undergraduates and about 450 graduate students. And so I'd like to talk to you a little bit about my lab and then jump straight into the work that I'm going to present, which won't be all of these. So we work in about 4 areas. I am trained as a microwave engineer, always working in the millimeter wave regime, and really interested in things that lend themselves toward the terahertz range and the boundary between that and optics, which is optoelectronics. So my group has produced a lot of content on and research on integration and packaging. We look a lot at passive circuit design, antennas and sensors, as well as materials characterization is really a critical part of what we do in order to try to reduce design times and to be more effective in implementing the designs that we come up with. On the integration and packaging side, we've been looking at nanowires for via applications. And we've also been looking at nanowires for their magnetic properties, for some magnetic applications and nanomedicine applications. And then we've been looking at 2 and 3D integration and packaging, as well as vertical transitions. For the passives, nanowire interconnects have some interesting properties, and they show a lot of promise for really high speed signals because of their potential to have really low loss. And the group has also worked a lot on just demonstrating a variety of ways to miniaturize other passive components like couplers and filters and high performance interconnects. We also do quite a bit of work on antennas and sensors. Today, I'll talk about some virtual arrays that we've been building, which I categorize in the realm of that can be used for free space interconnects. And we look at planar structures. And in the past, we've done some stuff with reconfigurability, in particular with RF fluidics. And then in the plane of materials characterization, these nanowires that I keep talking about, they really have grown in popularity for a lot of nanomedicine applications, and they really have some intriguing characteristics that I think may become important for us as we move into 6 and 7G applications, where signal strengths are incredibly small, and signal loss, line loss, circuit loss is a barrier to entry in that space. So I would say that my work really started off very subdisciplinary, and it has evolved into something that's more multidisciplinary and now interdisciplinary. So on the left, you can see just some illustrations of things that we've done. At the bottom, these advanced interconnects, which are like three-dimensional vias. We call them through silicon vias at the time. This is coplanar waveguide-based structures that we worked on a few years ago. Integrated packaging, like for advanced miniaturization of passives. And then also we looked at some techniques to do miniaturization of antennas where we could see substantial reduction at low frequencies. My work basically is equivalent to working on the nervous system of electronic circuits, and I've enjoyed that space quite a bit. A few years back, I also worked on a project that had to do with bacteria. I was really interested in how can we come up with biodegradable electronics. And so it turns out that, so sorry. It turns out that in the sensing community, and in particular with solar cells, it turns out that people use bacteria a lot to try to do current conversion. So I worked with a colleague in a local company, Optimec, to develop some electronic circuits that could be used to grow bacteria on them to understand what their electric current carrying capacity was. So that was a multidisciplinary project. And nowadays, I'm actually working on quite a few interdisciplinary. So one is related to cancer. The second one, which you see in the lower right corner, is related to how do we characterize or help ecologists understand the disease potential that can affect our forestry. Turns out in the United States, oak wilt is a really horrible disease that can attack oak trees. And we've all probably seen it, where you have this brownish looking color on the leaves of oak trees. It turns out that disease, that's a disease, and that disease, it propagates through the root system of those trees. If it propagates fast enough, it's really a problem for the US because 40% of our forests are oak trees. And so if we were to lose those trees due to disease, that means that our capacity to process a lot of the CO2 that we produce and to have shelter and all of the other things that go with nature, it would substantially change how our country would function from an ecological point of view. We're looking at developing microwave sensors to help the ecologists understand how the trees change as it relates to drought conditions, and then what happens to those trees if they introduce the medications that they create for them, if they can study the behavior. So you'll see from what I'm going to talk about today that those 4 areas that I talked about, materials characterization and circuit design, they all sort of play an intimate role in these applications that I'm describing here. So let's talk about what we're doing here. Today, I want to talk about low loss antennas that we've been developing for phased array applications, and that we've been able to demonstrate that these designs can also lead to free space chip-to-chip communications. And I think they have a lot of promise because, especially when you move up in frequency, signal loss is a big issue. So these free space chip-to-chip systems can alleviate conductor loss and basically have very close, they're sort of a close proximity or near proximity way to get signals from one plane to the other. And then I'll finish the talk by talking about nanomedicine and what we've been doing with nanowires, in particular magnetic nanowires. So in the development of the virtual antenna elements, or these arrays, there are three things that we care about. You want to make an antenna point in a very specific direction so that it has high gain, but you also want the aperture, which is basically the surface of the antenna, to operate efficiently. An antenna's job is sort of like our ears. Its job is to convert an electrical signal from inside of a black box to a free space signal that can propagate. And when it does its job really well, it means that all the energy that gets to that antenna can then be released into free space to propagate with not only the carrier signal, but also the information associated with it. At the same time, you'd like it to have low loss, because if the energy gets stuck in the antenna, that means that the signal that comes out is not going to be very strong, which means you have to have a lot of repeaters in different locations to compensate for that loss. And you also have signal degradation. So it turns out that in 1924, we actually, had mobile communication. So this is not a new idea. And it turns out that was like 100 years ago, right? So when we think about where our devices have been going, we have these three C's: communications, computing, and communications. And yesterday, all of these were discrete components, but today they're all integrated. And what we're finding is that because mobile communications is extremely integrated, we've been over the last several decades looking at this significant progression in the capability of the hardware that's in these devices and the requirements that this particular software, these hardware and software have to have in order to accommodate a variety of functions, meaning the co-integration of those three C's, and then being able to manage that information, to get that information off of a device to other devices. So that pushes us toward the need to have 5G and 6G, primarily because at the turn of the century, 1999 and 2000, we were just dealing with how do we go from wired to wireless more efficiently and effectively while the internet was evolving. But it turns out that now our challenge is that we are at a point where people are trying to not only talk to each other, but we know now that in about 10 or 15 years, that the number of devices that are going to try to talk to each other are about a factor of 3. So if you think about a factor of 3 for the planet's population, so if you think about our population being a little over 6 billion, imagine that many connections and having an infrastructure that can support that. So what you'll see here is the fact that our infrastructure is having to become quite complex in order to accommodate the fact that we have and will have significantly more connections, whether it's people to things, or things to things. And this is just an illustration of what that infrastructure looks like today. What we know is that that's not sufficient. And so in order to make things in order to move toward a system that will accommodate this rapid growth, what we know is we can go up in frequency that makes everything smaller, which is nice, which promotes mobility, but it also gives us more channels. If we can get the resolution small enough to meet, our federal government requirements for the FCC of, about 100 megahertz for a channel, and if we can design circuits that can give us the appropriate quietness when things are supposed to be off. But we also know that because of all of these devices and because of the location, it would be extremely difficult if you try to expect all devices to connect to things that are locally on the ground. So this picture is just an illustration of something that I thought was really fascinating, is the idea that not only are we becoming as mobile, or are we the mobile devices in our communication system, but our communication systems themselves are more likely to now start becoming mobile. You have satellites, which have been here for many, many years, and you have ground stations. And of course, we have routers and things that we're familiar with today. But the idea, because of integrated circuits and these small chips, is that now that we have drones and we have lightweight technologies, these drones can potentially become a mobile communication infrastructure that can move as needed to the locations to provide temporary or spontaneous communication. So now we're at a point where airborne communication networks can become a part of our infrastructure. And what that really means is that we need we need a better ability to route a signal to a specific location, hence to be able to use phased arrays. So I just want to give you a simple example that when I talked about the oak trees and the wilt, my colleague who does research on that, they actually use drones to go overhead to do remote sensing. And this is an example. So what you'll find is that, we have communications that's occurring at short distances to really long distances. And that if we were to use mobile devices like UVAs, you can see that this can increase substantially. And the ability to have antenna systems that can beamform and scan in a phased array configuration are essential if these devices are to also talk to things that are on the ground. The last thing I want to point out, and this is a graph I got from my colleague in my department, Yaya Tusi, it really talks about the effect of power. And that's where I think we need to be thinking as we move up toward the terahertz regime, which is around the sub-terahertz, which is around here. We can have really, really pointed beams if we have really large arrays, and purple represents the largest. So at about 60 gigahertz, we have demonstrations that people can do arrays of this type. But as you move up in frequency, you'll start to see that our highest demonstrations when we get into this regime are in around about 16 elements. And then once we get in near in the sub-terahertz range, which is in this several hundred gigahertz regime, we're down to like 1, maybe 4 elements. And a lot of that is because we don't have the ability to radiate power very far. And these R's represent the actual distances that things can travel. So it becomes important to figure out how do we reduce loss so that the slope of this curve can actually move up with power. So what my group has been doing is we've been looking at antennas and trying to find ways to develop concepts to develop better beams and to get more gain and less loss in these systems. I'm going to show you some work that we've been doing around slotted antennas with Fabry-Perot cavity. They're Fabry-Perot cavity antennas that have a lens on top. And if you look at this picture, this is just a simple example of a typical slot antenna, except it's cavity back because we want to radiate it only in one direction. So the bottom of this is a box that's all metallic. And then this slot is the antenna. It radiates up and it creates a beam that looks like this if you're about half a wavelength above the surface of this antenna. When we talk about arrays, for example, a 2x1, then you could take this same structure. You'd have to have 2 feeding elements. So this is one feeding line. This is another. It radiates through to the other side. So this is a top view, and it produces these 2 beams in the near field. But one thing you can notice immediately is that the beams themselves are not well formed. You can see that the distribution of the signal, rather than having a beam in the middle so that it's Gaussian, is that the beam is really distributed and the intensity varies quite a bit. What we found is if we took a structure like that and put a lens on top of it, that we could take a beam like this, which is a little bit not well behaved, and we can create a beam that looks like this, because now this beam is more like a Gaussian. So you can imagine that this is going to come up and come down where the peak is in the center. And this gradation is relatively symmetric. This tells us a couple of things about the antenna. It tells us that this antenna is that the lens, if you think of the lens sort of like our eyeglasses and the antenna sort of like a light, it's as if it's the light coming through here, through the lens that focuses on this plane that you see here, which we call the near field reference plane. This lens is actually responsible for shaping this structure. And what happens is that when a signal comes from this antenna, it radiates like this. But this lens has the ability to make little bitty radiators. So you can imagine that each one of these slots is a little bitty radiator, and that they are all more or less uniform enough in each of the locations that at this distance they add up and they give us this really nice, well-behaved shape. What we've also been able to do is one of the things that tends to happen when you're dealing with any kind of antenna or an array is there's concern about what the field looks like from a phase point of view across the structure. So if you look at the black curve on the left, for a single element without a lens, what we can tell you is that from one side of the structure to the other side of the structure, the phase associated with that energy varies quite a bit. It's plus or minus 45 degrees. If we would like to see things behave as if they are linear and like a plane wave, you really want to see this be flat, because it would suggest that the signal from the left side to the right side more or less has the exact same phase orientation. So when we put the lens on it, the lower curve shows you that the red, which is shown in the red, it shows us that we get a much, much smoother flat response, which is more like plus or minus 9 degrees as opposed to plus or minus 45 degrees. So this is really encouraging. What we've also been able to do, which is equally important, is that we are also able to now take that same idea and we can use a similar kind of lens, and we can actually create two separate beams. And we can see now that the two beams are also very similar in shape, which means we have projected from below one antenna that projects these two spots above, and these two spots now act as a 1x2 array. So what you'll see here is this curve here is when I have an FSS, and this variation is when I don't have an FSS. Let me go back a slide. So I showed you the data here. This is the data without the FSS, which is basically two separate antennas that are fed by two separate feed lines. What's interesting about this structure is that this structure has one antenna at the very bottom that feeds through a FSS and splits the beam into two locations. And these two locations now give us this really clean beam that then gets added back up later. So let me show you the gain. So the gain for this antenna, both of them left and right, the black is the design based on the antenna by itself without the lens, and the red is the same design with the lens. And what you see is that we're able to enhance the gain because we're able to increase the efficiency of the aperture, the surface of that structure, and that efficiency, because that is a more efficient aperture than the beam in the far field. So now this is at a distance from the antenna. The beam at the far field can actually work in cooperation so that we can collect all of that energy and come back and end up recapturing the gain that's associated with that structure. So what we found is that for our virtual designs, because the projection is at that plane that I talked about previously, we can see an increased aperture efficiency of about 85%, which is excellent for these kind of structures. And the gain associated with those then has a gain increase of about 4.5 dB. And similarly, for the two element structure, we see about 4.8. So this is a huge improvement, which kind of says you can really take one element and clean it up just by putting the right kind of lens on top of it. We then wanted to do a comparison, because when you think about that virtual design that I'm saying, use one antenna but split the beam with the lens versus two antennas and two feed lines, we wanted to understand what happens in terms of signal line loss. So here's the feed line structure. The first one is the feed line that comes off the back. And the second one is the solid line. The dark one is the FSS. What you want is to see this red line move up. What it shows us is that the loss is just associated with the feed line, which are kind of shown in these pictures on the left, that the losses indeed do reduce. And what we're seeing is that we get about 3 dB back because we've eliminated the feed line paths in the other two structures. Now, so this is a summary of what I talked about. I discussed the first and the second, but we also have examples where we've done a 1x4. And even in this structure here, we're taking a single element that's located in the middle, and we're splitting it into these 4 quadrants here. This is going to also produce a much more narrow beam in one direction, but it's a structure that won't have the feed line losses that are typically associated with a 2x2 array.
Dr. Franklin?
Yes.
My name is Keith Tinsley. I work closely with Homer and a lot of others here on the call. I just have a question. I apologize for being late. I had some personal issues I had to take care of. But is there a law of diminishing returns, so to speak? How small can these radiators be within a defined cavity, 27 by 27, keeping the same lens or focus structure? I mean, have you investigated how small these radiators could be, and you still could achieve the same type of antenna patterns that you're showing here?
So you're seeing an optimized structure. So this 27 by 27 is a small, is the optimum for this particular structure.
Okay.
What matters in here, I mean, you could make many, many more of these, but it's not necessary. What you care about is the unit cell. And when you model the unit cell is going to give you a response that kind of tells you how much this structure is a leaky structure. So this unit cell will give you a hint of how much energy will leak through before this cell becomes invisible. So all of these can have, if you have an infinite number of these rectangular cells, there's a point where you have no leakage, then the leakage increases until finally there's a self-resonance where it's as if the lens is not there at all.
Okay.
So that's very much a function of your dimensions here. Now you could go and add more, but adding more isn't necessarily better.
Right.
What matters is what matters is how much leakage you want to have. And then you design the rest of it around the leakage. So in these, the leakage is about 0.8 dB at 12. And what's important about this structure is this is a scale model. So we've intentionally picked 12 gigahertz. Our intended application was an RFID problem for some blood sensing work we were doing a few years ago. And there we wanted 60 gigahertz, but 60 gigahertz would be too difficult to do for prototyping and studying. So we're
because of the dimensions involved, or just
more manufacturing. I mean, I can send my students to the lab and they can machine mill these, which is what we do. Whereas if I wanted them to do 60, I'd have to send them to the clean room. And we would probably spend more time doing process work than design work.
But this type of structure is feasible at those frequencies.
Absolutely. I'm going to show you a little bit of that in a second. Yeah.
Okay. Thank you very much.
So this is definitely scalable. What's beautiful about this structure is that it's absolutely scalable. And
it totally looks like a phased array antenna system.
Yeah. So in this next piece, I just want to show you an application of this lens. So I talked about the eyeglasses, the lens, plus an antenna. Last one was a slot. This time I'm going to use a patch. And in this case, this is a patch to FSS, but I'm using this now as a free space vertical interconnect. So VI just stands for vertical interconnect, and FP stands for fabric Perot cavity antenna. So in this picture, what we do is we have a structure that's set up like this, and we illuminate this cavity, and we leak some energy out. And at that plane that I've been talking about where you see the pattern distribution, it's right here, this gray. If we put a pickup antenna right near it, we can pick up the pattern, which is that focus signal, and we can actually go from an interconnect to a free space signal, focus it on the lens, and then focus it through the lens to this gray space. And then I can pick that signal back up and convert it to a guided wave structure. So that's what I'm going to talk about briefly here. So this is sort of the configuration I just talked about, how we have an antenna that then radiates up through the lens and it's picked up by the patch. This is the dimension. This is the cross section. These are the dimensions, and this is specific to 12 gigahertz. Both of the structures are on 2.2 for the epsilon R. So we've talked about this already. You know what that looks like. If you look at this picture on the left, this is a simulation of what the response would look at a specific frequency, which is 12 gigahertz. And what's important here is just to be able to see that this W is the width of the rectangular slot. So we can tweak this a little bit by altering that between 0.5 millimeter and 1 millimeter. And what that really boils down to is we're trying to deal with the insertion loss. So I can reduce my insertion loss by altering this dimension. So at 0.1, I get less loss than at 0.5. And what we find is that if I increase the width just a little bit, I can get a little bit more bandwidth at that frequency, because this is a frequency selective surface, hence it's inherently discriminating. And in this work, we used an SMA connector, and we found that, we get these additional notches over here and here, which was to be expected. But in this case, I'm really only interested in what's in the circle, and I'm not interested in what's out here as an interconnect. So we wanted to test that idea against a conventional a microstrip to via interconnect structure. We have a 2-wire system, so basically showing that, of course, if you use multiple wires, you get parallel inductances, which reduces the inductance and resistance. So by having multiple wires, I would expect my insertion loss to improve, which is what this shows. I have 2 vias instead of 1. So I can reduce this as much as possible. And now I want to compare that to my structure. They both have the same feed line lengths, except I have an antenna at the bottom and an antenna at the top in the next one. So what you'll see here is the dashed line is a straight through line. So it's just a straight microstrip. And then the blue line is the 2 via from the previous slide, where you see here. And the black line is our vertical interconnect. So this difference between the blue and the black really represents the what I save in terms of loss by alleviating having those 2 wires come up through the board. So this antenna structure now serves as my vertical interconnect, which gives me something that's very close to a straight line if it were on a planar surface. So here you'll see the details written over here. And the bandwidth was about 8%.
And what about the phase dispersion over that bandwidth?
So I don't have data to show that, but if I remember correctly, the phase is fine.
Okay.
Because we have because we are projecting such that we have a plane wave. I talked about, you probably weren't here then, where I talked about how flat the phase is. I'll go back to that shortly.
No. Please proceed. I could catch up.
So here is a simulation of the 60 gigahertz version of that free space interconnect. And so I wanted to just point out that we're able to demonstrate that when we just scale our model up to 60 gigahertz, we get something that's quite close. We're about a dB now relative to the through line. So the through line is 1.04 dB at 60. We're 1.6, so we're just a half a dB higher, which is much lower than what it would be if I use that same vertical interconnect with vias. We're in the process right now of actually building a 60 gigahertz version of that. So I'm hoping in a couple of, in a month or so, we'll have some data to kind of confirm that we can that experimentally it responds similar to what we're observing in the simulation. But we've been very happy with the fact that this particular approach to the problem is a scalable approach. All right, so summary. This particular section was about free space interconnects using that Fabry-Perot cavity antenna system. What's unique about our work is we have a really simple design. Typically, when you want to see this kind of phase profile, what people do is they take electromagnetic simulations and they spend a lot of time varying the slots along the perimeter to try to get the waves to add constructively so that you can get this response. We have figured out a way to more or less use a very simple rectangular structure and optimize how that structure is scaled in itself, and then combine so that we can get this natural coordination of the signals working together to form this Gaussian beam. And then these are the things I've already talked about before. So I have about 20 minutes, and so I want to shift gears and talk about this nanomedicine application. And so in order to leave, I think I'm supposed to stop at 3. So what I'm going to do is I'm going to skip through some parts because it'll take longer than we have time for, but I'll try to get to the essence of what we're doing with this work. So the big thing is, and the great thing is, you guys build things. So this is a better conversation than when I have with people who don't. Essentially, like, what is a nanometer, right? So relative to what we understand, a pen is a millimeter, pollen is about 20 microns, and blood is about 2.5 microns, and then carbon nanotubes are about 2 nanometers. I'm going to talk about nanowires that are about 40 nanometers. And then one of the things I want you to just keep in your mind is that I think that the future for a lot of what we're going to do in the comm space is going to absolutely depend on nanotechnology. And I am working on some aspects of that, but it's not, this is a, I'm sort of way out there. So if this seems way out there, it's because it kind of is, but I think that it's very important, and it will become more obvious in the next decade, I believe. So one thing to note about nanotechnology is in the 50s, everything was based on individual topics. And what we're finding is that over the years, I came in the game around here. I wanted to try to start thinking about it at that point, but nothing was mature enough that I could show in our field. But 20 years later, all of a sudden now a lot of things are converging, and now we're starting to see applications with nanostructures, nanotechnology, in a variety of ways. And so molecular systems are really the most popular right now. But I think as we move to sub-terahertz, we're going to see we're going to see a need for knowing how to do this and what to expect when we get there. So I want to talk about some work that my student Yali Zhang has been doing. And this is a very close collaboration between myself and a colleague, Beth Stadler, who's a material scientist, and her student, Joseph Young. The goal of this project was for us to build a microwave spectrometer that would allow us to measure ferromagnetic resonance of those nanowires. They wanted to use the nanowires for cancer research. They basically, and I'll talk about that in a second, we wanted to see how you could do it, but also could we come up with ways to enhance the signal so that we could ensure that the ferromagnetic resonance that we were measuring made sense. So this is a picture of some cells. These are cancer cells from a dog. And just to acclimate you, the red is the membrane of a cell, the blue is the nucleus of a cell, and the green are nanowires that are in the cells somehow, some way. We want to use the wires to tag cells. And the way they tag cells is you put a coating that's the opposite of what you're attracted to in the cell. And then that coating will, if what it's looking for is in there, it will migrate to it. And we can know because of the attraction of those two things that the particular feature of a disease is present. So this is a bigger picture. I knew not, I couldn't remember my biology, it was so long ago. But I just want to tell you that, modern day biology, we're kind of at this point. Here's the nucleus that I talked about. Here's the membrane that I talked about. And there's a whole lot of stuff in a cell that we never talked about when I learned about cells. But the one piece that's important in this picture is the idea that there's something called an exosome. And in an exosome, essentially an exosome is considered to be the garbage bag of a cell. So all of those other things that I talked about, they kind of coexist. But what happens is cells will regularly push the trash out of the cell. And when they push the trash out of the cell, scientists in that community want to understand what's in the garbage bag. For them, it helps them to understand what was going on in the cell. This work was about trying to understand if we could tag the garbage bag and then understand from the medical science side, what was in the bag, because the coatings on the tags, these nanowires, would give you a hint that whatever they were looking for was in that garbage bag. And then the other thing that they cared about, which is way, way out there from where we are right now, was when cancer spreads. Right now, they don't know how it spreads. They just know that it spreads, and they kind of know how it's loosely connected. Ideally, you could have these tags in there, and you could track how the cancer moves, and you could determine what parts become, more challenged and metastasized or not. So way on our side, the engineering side, is understanding this one little feature about a magnetic material called its ferromagnetic resonance, and then how to actually make that measurement. So the FMR condition basically is you put a DC field and an AC field together, and when they are perpendicular to each other, at the right combination of magnetic material will absorb the AC signal, our microwave signal. And I'm looking for dips in the microwave signal. So, and then just loosely, this method that we're talking about, this tagging of cells, would be very similar to sort of a nanoscale RFID system. So this would be nanowires. They are formed in a matrix of alumina. It's aluminum, anodized aluminum oxide. And you can grow any type you like, iron, nickel, or cobalt. The ferromagnetic resonance is a function of its diameter as well as its length and its type. The coarse information comes from the type, but you can get some fine resolution information by looking at length and diameter. And these are the ranges. The ranges can be anywhere from 15 to 300 nanometers. These are the spacings of interest and the heights that people can typically do. And you can buy this type of material to grow them. So you can have one wire or many wires. It's called a nanowire if the length to the diameter ratio is bigger than 10. If it's less than that, it's a rod. And if it's less than that, it's a disc or a sphere. And then because they grow in a material that has a crystallography, they will have this kind of separation, this hexagonal separation, which is important because it tells us how magnetic fields between the different wires interact with each other. So if I put a magnet and an AC field together, then I'm going to get a ferromagnetic resonance. And what we were doing is we were interested in studying how does one go about doing that and how do you ensure that you've done it accurately. So this is just pictures of the different materials that we started with. This is what they look like on the surface. This is what it looks like when you cut this plane. And we essentially grow, this is upside down. We grow the wires from, we put a metallization here. The pores go all the way through and we grow metal into the wires based on the particular porosity and pore size of the matrix that we're purchasing. So we studied these two samples, a wide one and a thin one, 72 and 80, and they're both for cobalt. And then this is just our measurement method. Two takeaways from this is I can hold my DC field constant and sweep my AC field, or I can hold my AC field constant and sweep my DC field. It turns out that when we do that, there are different features that come about. I would like to point out that there are two things that really you want to know when you look at data like this. There's something called out of plane. This is the magnetic field. When the magnetic field is orthogonal to your sample, that's considered out of plane. When the magnetic field is in the plane with your sample, that's called in plane. It took my colleague and I about a year and a little bit to realize that when we said this, we were not thinking the same thing, which was interesting. So what we found is that this green line is what theory predicts, and this red line is what we measured. So we were happy to say we know how to make that measurement with confidence. What we also found is that when you're making these measurements in a coplanar waveguide design, which is what we use for our test circuits, that it matters where you place the sample. So we did some studies to understand how much it matters and why it matters. And so in the next one, what you'll see is if you just put your sample of interest over the slot, we want this dip to be larger. You can get a lot more signal strength than if you were to put it straight over the signal line. And that's true because when you do simulations like an HFSS, the field intensity is much higher in the slots compared to the metal electrodes, which is above or below the metal electrodes. So you can get a lot more energy absorption because you just have more energy focused in these domains. And then we looked at some things to look at, and this is just an illustration of that placement effect. Now, one of the things we also found is that we wanted to sort of trick our circuit, right? We know what happens if we only had wires going from one side, but it turns out if we put a metal layer on the back, we can create a reflection. And so the signal intensity that goes up, this wave just keeps rotating and then it comes back on itself. So now all of a sudden I can detect a much stronger signal. This is my signal is going into the page that we're looking at. I can detect a much stronger absorption of my signal if I let the signal go up and reflect back down. Remember, FMR is the frequency with a certain DC. So this is DC. FMR is the AC frequency, which is 40 gigahertz in this case. It's the AC signal frequency that absorbs my signal. So ideally, if this were a regular transmission line, this would be straight. So whenever I see a null, that means that my wires have absorbed some of the signal that was going, that was passing through them. And that absorption is the FMR frequency. So what this showed us is that if I don't put metal on the back, I get a weak, I can still see it, but it's very weak, see 0.005. But if I put that reflector on the back, I can get 7x enhancement. And now I can really see the presence of the FMR. And this picture on the right just kind of shows you why. Because now I've got all this energy that's coming up and back. And it turns out that that actually is what's affecting over the signal line now because of the reflection. So it's almost like a microstrip behavior above that electrode. And then there's a angle dependency, which is what this plot shows. And we were able to, these are measured data. So we've been able to prove that this does actually change with respect to the angle. And this is the proper type of change that one would expect. So we know we're not measuring circuit resonances, that we're actually measuring material resonances.
So is there any concern with toxicity using these cobalt and copper?
So in a diagnostic sense, no, because if I'm taking cells out of someone and I'm
I got it.
It's fine. If I'm doing it in a living system, the one that is okay right now are iron coated. Coated iron is okay biologically and approved by FCC, and that's a sphere. So then if we move forward, what we can see now is we actually came up with a new method for identifying the FMR. Most people tend to use the magnetic field, and you'll see that the signal strengths are really tiny. So you have to have a pretty good understanding of what you're trying to do when you make these measurements. What we found was that if we look at the phase of my transmitted signal and we take a derivative of that phase, it turns out that I can see quite sharply different frequencies. And now if I sweep my DC field and I look at those and I look at that data for fixed AC signal, I can see the peaks and their progression. And these resonances are equivalent, these points here for the resonances, they are equivalent to what I showed you with that Cattell equation from the beginning. So this is a different way to observe the response. And it's a nice way if you just want to get a quick and dirty measurement. And then finally here, we can come back and we do a comparison. So this is the FMR versus Cattell using that magnitude in the PAM method. I want to end by just saying two things. The magnitude method works pretty well in most, it's just a classical method. What's unique about, so the challenge point for the magnitude method, the MM, is that whenever the two modes actually tend to overlap, it's difficult to tell where the FMR is when you get close to the DC field, zero DC field. So we know something's in here, but we're not quite sure where it is. With the PAM method, that actually becomes much more apparent. Turns out that this turn here and the turn here represent a change in the moment. So we can tell by the way this points, the moments in the wires are either pointing up or they're pointing down. So we get that differentiation, which you don't get with the magnitude. But we also get clarity at these two endpoints, which are what's happening right here and here, that this really is the ferromagnetic resonance point for this particular field here and here. So that was actually a nice discovery in the work that we did for this problem. And then lastly, because we are interested in tagging, the idea becomes, if I were to put two things together, can I identify what they are? And the answer is yes. It turns out that if I were to measure nickel and cobalt together, if I have some prior knowledge about what is nickel and what is cobalt, when I put them together, I can actually detect that they are both present. In that nanomedicine application, that would allow them basically to do simultaneous measurements. Right now, everything's quite serial. You take a drop, you do one test, you take another drop, you do another test, you take another drop, you do another test. This would say I could attach the antigens to my different samples, put them into one sample, run them through the scanner, and I could detect these different peaks. And I could tell you that, yes, cobalt and nickel are both present, or only one is present. But in the characterization of those structures, like what we were doing, we just want to see how sensitive they were in the host when we look at a stacked or a serial case. And what we found is obviously that when you stack them, depending on the moment, one will be stronger than the other. Whereas if you place them in series, they all see the signal at the same levels because they're on the same at the same plane. So you can detect them both quite easily. And then again, with the PAM method, we saw if we did that together, we could see this kind of we saw this kind of differentiation. So this was the PAM method when we put them all together. So it's also another clever way to identify the presence of these 3 different materials. So I want to just end on why would a microwave engineer care? Well, it turns out that there's some work already being done on nanowires in aluminum oxidized substrates that are showing some promise for the commercial. My group is also working on this, but we're working on it actually with integrated circuits. So we have a project. I'm not talking about it in here today because it's still ongoing, but that project we have developed a way to integrate this aluminum oxidized material onto a silicon substrate, and we're looking at it for interconnects and for vias. And therefore, if I want to use circuits, what do we care about in our field? We care about permeability. So I'm going to skip this and just go to the bottom line. The bottom line is that you can actually use the information from the ferromagnetic resonance to understand what the permeability looks like. And you remember I talked about when you make those measurements, you could do it with and without a copper layer. So if you don't have the copper layer, you'll get these responses that you would extract out of your transmission data. And you'll see that these curves are kind of all over the place. This is the real part of the permeability. This is the imaginary part. And so what you'd expect is to have a well-behaved series of lines, but because the signal strength is so low, you get quite a bit of variability when you're trying to extract that information. By adding that copper layer to the back, we now have a trend line that shows us that if I increase my DC field, this is the magnet, and I measure my AC response, my permeability for these nanowires varies. And so we're able to see that the permeability for this, I think it was 12% or 20%, that we're able to go from 5 to about 7 in terms of the real part, and the associated ferromagnetic resonances, which are these peaks, are going to vary similarly. Generally, you want to operate your magnetic materials on this side of your structure. You want to operate just below the peak imaginary part, because the peak imaginary part is where the signal is absorbed the most. And so this gives us a hint of how much we can reduce an electronic circuit, because this is now, instead of having mu r equal to 1, we can now have mu r that ranges from 3.5 to 7, and you can do those in an integrated way. So I want to close that out by just pulling all of this back together. These are the various plots that I've shown you over the course of the talk. The cobalt nickel nanowires can have permeabilities up to 7, but they have imaginary parts of 4.5, which is going to be an indication of the loss. And I just want to thank the various groups that have been responsible for those 2 very different types of projects that I've talked about today. Thank you.
Thank you, Dr. Franklin. That was very interesting, amazing research, and I see you talked about a lot of the applications that come with it, and it's really exciting what technology is going to bring into the future. So really wonderful. So if you have any questions for Dr. Franklin, we still have a few minutes. You can either type them into the chat, or you can unmute yourself and ask her directly. Either way.
I see Alex's hand.
Yeah, Alex has a question. Go ahead, Alex.
Well, a couple different things. One thing is, used to work with planar arrays a long time ago, and a frequency like you show for another application, more for military application. But we used to use a Wheeler technique, and it had to do with the reason that when you have a steered array, when you steer at wide angles, the impedance varies, and that cross coupling kind of eats your lunch on bandwidth. Had you done any studies on that, where in that solution it's a dielectric layer instead of a metal aperture layer, but using your metal aperture technique, do you get a better impedance consistency when the beam is steered to really wide angles?
So with these, we've just started looking at the actual steering piece, and because they're so narrow band, the steering, at least for what we're showing right now, is quite narrow for a single layer. If you want to have so we're, I think my student and I were looking at it. I think we're at like either 15 plus or minus. So that's not particularly wide. In order to get wider steering, we actually have to do multi-layer stacks for that. And so I don't have a direct answer to your question, but I agree with you. That is a challenge if you want to actually, if you're going to start trying to steer. We've been looking at multiple techniques that allow you um, to create the steering. There's one where you can actually put like a disc on top that you rotate, and that rotation of the disc causes the beam to. Can you see my hand? It causes the beam to do this. Yep. But not this. And I think you're talking about the steering in this direction, that there's going to be a limitation. These will not allow you won't be able to do broadband steering, more focused steering, I believe.
Yeah, I was talking about like broad angle steering.
Yeah, you were talking about here, broad angle steering, correct. Yeah. But the one that someone says the moving. So with the one that moves, it turns out that the application we were looking at, they actually have a pivot point in the center, and there's a thing underneath that actually spins the second layer. I'm probably not describing that very well, but anyway, it's an intriguing idea because we were also trying to figure out, okay, if we were going to steer, we were thinking about how do you come up. There's some techniques I've seen where people can do sliders on top of the FSS so we could change the dimensions of the slots. But this one is actually using a second layer and then having that rotate where from a center point in the middle of that structure.
Oh, thanks.
Mm-hmm.
There's another question from Michael Duncan. What was the effect on separation between the lens and the antenna?
So this is a kind of a classical problem, right? Your distance from the lens to the antenna is essentially that you need to have half wavelength, and it just depends on the cavity. So if the cavity is empty, now in our case, remember the lens has a little bit of dielectric underneath it because it's on that 2.2. So you need to know what's the effective dielectric constant in the cavity. But your height separation is basically a half a wavelength. So that what's happening at the interface of the antenna is projected precisely to the slots so that that energy can actually leak out. Did that answer your question? And so if you're off, then obviously you're not going to, if you're off, what's going to happen is your frequency that radiates will be smaller, different, but you also have to have if your antenna is really narrow band and you are off in that height, then you're not going to project, you're not going to get, your signal that comes out is going to be off. So you almost need to make sure that the error between the height separation and the bandwidth of the antenna that you're working with can accommodate that swing. Because let's say I'm gonna make up a number. Let's say you have a 1 gigahertz antenna, but your height is off such that, your height is off by, I don't know, if you have 1 gigahertz antenna with say 10% bandwidth and your height is off by enough where it's a half a gigahertz, then you won't see that antenna, right? Because your antenna swing is only, it's only 5% on either side of 1. As opposed to 5, it's only 1%, 0.5% on either side of 1, as opposed to 2.5% on either side of 1.
Well, it looks like we don't have any more questions, and then we're also kind of at our time. So I just wanted to take this opportunity to thank you again, Dr. Franklin, for being with us today, sharing all the different facets of your research, and we're looking forward to more collaboration with you. On a variety of different things that we talked about earlier. And thank you again for your time, and we'll hope to see you soon.
Thank you very much. I appreciate the invitation and the great questions.
Yeah, thank you. Thank you for the deep dive in an hour. Appreciate it.
No problem.
And hopefully this is a beginning of a broader discussion. So we'd love to continue the dialogue.
Thank you. Looking forward to it. Okay. Bye-bye.
Thank you.
Bye. Thank you.
Bye. I like the flashing.
Bye. Have a lovely weekend, everyone.
Bye.
All right. Give thanks.